we need to talk about what happened on November 5th, or more accurately, what did not happen. After months of predictions, calculations, and anticipation about what 3I-ATLAS would look like, emerging from behind the Sun, after its closest brush with our star, the images finally arrived, and they show something that should not be possible if this object is what we have been told it is. Before we dive into this, I need you to do something for me. Hit that like button, and if you have not already, subscribe to this channel. We're tracking the most significant interstellar visitor in human history, and you will want to be here for every single development. And speaking of developments, tell me in the comments where you're listening from right now, what time it is there, and here is my question for you. Do you think the missing tail is proof of artificial propulsion, or is there a natural explanation we have not considered yet? I genuinely want to know what you think, because this community has some of the sharpest minds analysing this object. The Arnaves Observatory in Spain captured 3I-ATLAS on November 5th. The Virtual Telescope project did the same. These are not amateur operations, these are sophisticated facilities with decades of experience photographing comets. They know what they are looking at, and what they captured was a compact source of light, a fuzzy ball with a coma around it, but no clear cometary tail. None. The images show essentially the same morphology we saw back in July when Hubble photographed it. Before perihelion, before the intense solar heating, before everything that was supposed to transform this object into a spectacular display of cometary activity. Now let me be very clear about why this matters. This is not about aesthetics or missing out on a pretty picture. This is about physics. This is about what the laws of momentum conservation tell us must happen when an object accelerates without gravity alone explaining that acceleration. And 3I-ATLAS did accelerate. NASA's Jet Propulsion Laboratory confirmed it. The data is public. The non-gravitational acceleration was measured and it is robust, standing at 3.7 standard deviations. That is not noise. That is a real signal. The acceleration has two components: a radial push away from the Sun at 1.1 times 10 to the -6th astronomical units per day squared, and a transverse component, perpendicular to the Sun's direction, at 3.7 times 10 to the -7th astronomical units per day squared. These numbers might sound abstract, so let me translate them. This acceleration, if caused by the rocket effect of gas jetting off the surface, means 3I-ATLAS had to lose more than 13% of its total mass during perihelion passage. 13%. That is not a thin layer of frost evaporating. That is a substantial chunk of the object's entire bulk. Avi Loeb calculated this using straightforward momentum conservation. The mass fraction lost equals the perihelion passage time multiplied by the acceleration divided by the ejection speed of the gas. The perihelion passage time is about 1 month, the time it takes to cross the spatial scale of its closest approach to the Sun, the acceleration we just discussed, and the ejection speed, for a natural comet at the surface temperature 3I-ATLAS would have experienced, is around 300 meters per second. That is the thermal speed of molecules sublimating from ice heated by the Sun. Plug those numbers in, and you get 13% minimum mass loss. That is the floor, not the ceiling. Now think about what 13% mass loss means in practical terms. If 3I-ATLAS has a nucleus roughly 5 kilometers in diameter, which is consistent with the observational constraints, and it lost 13% of its mass, we are talking about at least 5.5 billion tons of material ejected into space. Billion, with a B. That gas does not just vanish. It forms a cloud, a massive coma of dust and gas that gets pushed by solar radiation pressure and the solar wind. That cloud should be obvious. It should be enormous. It should have formed a tail, a classic cometary tail, streaming away from the Sun, visible in any half-decent telescope image. And yet, nothing. The November 5th images show a coma, yes, but it is not significantly different from what we saw in July. The morphology has not changed dramatically. There is no massive tail. There is no evidence of the kind of outgassing event that would be required to produce the observed acceleration through natural cometary processes. Let me put this in perspective by showing you what we should be seeing. On November 3rd, just 2 days before 3I-ATLAS was photographed, the same Arnaves Observatory that imaged 3I-ATLAS also photographed Comet Lemon, a regular comet from our own solar system. Lemon displays a clear, obvious, textbook, perfect cometary tail pointing directly away from the sun. This is what comets do. This is what they look like when they are actively outgassing. Lemon is not special. It is not extraordinary. It is just being a comet, doing what comets do. 3I-ATLAS, according to the acceleration data, should have been outgassing far more violently than Lemon during perihelion. It should have lost over 13% of its mass. It should be surrounded by a cloud of material orders of magnitude more massive than what Lemon is producing. And yet the images show less activity, not more. The tail that physics demands should be there is simply absent. This is the contradiction we're dealing with. The math says one thing, the images say another. Both cannot be true if 3I-ATLAS is a natural comet. Now some of you might be thinking, maybe the gas is there, but we just cannot see it. Maybe it is too diffuse, too spread out, too faint for the telescopes to detect. But that does not work. The mass loss required by the acceleration is so large that the resulting cloud would be detectable. We detected the much smaller plume of carbon dioxide around 3I-ATLAS back in August, with SphereX and the James Webb Space Telescope when it was much further from the Sun and much less active. If there were billions of tons of freshly ejected material surrounding the nucleus now, post-perihelion, we would see it. The absence of evidence here really is evidence of absence. Let me walk you through the timeline to make this even clearer. Between July and September, 3I-ATLAS was observed continuously. 4,022 data points from 227 observatories around the world. During that entire period, the object showed no detectable non-gravitational acceleration. 0. Its motion was entirely consistent with the trajectory determined by gravity alone. Then came October. 3I-ATLAS approached perihelion, swung around the Sun, and suddenly the acceleration appeared. The object deviated from its predicted purely gravitational path. The Atacama Large Millimeter Array detected that 3I-ATLAS was 4 arcseconds away in right ascension from where it should have been. 4 arcseconds of displacement that gravity alone cannot explain. This means whatever caused the acceleration happened at perihelion or very close to it. That timing is important. For a natural comet, perihelion is when solar heating peaks, when surface ices sublimate most violently, when outgassing is at maximum. So the timing fits the natural explanation. The problem is that aftermath does not. If the acceleration was caused by a massive outgassing event at perihelion, then the gas from that event should still be visible now, just days later. Gas does not just disappear. It spreads out, it forms a cloud, it gets pushed by radiation pressure into a tail. We should see it. We do not. This brings us to the uncomfortable question that Avi Loeb has been raising consistently. If the acceleration was not caused by cometary outgassing, what caused it? There are not many options. You can accelerate an object in space through gravity, but we have already accounted for all gravitational influences, and they do not explain the observed deviation. You can accelerate through the rocket effect of expelled gas, but that requires the massive gas cloud we are not seeing. Or you can accelerate through some other propulsion mechanism, an engine, technology, something that can produce thrust without requiring 13% mass loss through natural sublimation. Now I know what some of you are thinking. This sounds like we are jumping to extraordinary conclusions, and you are right to be skeptical. Extraordinary claims require extraordinary evidence. But here is the thing. We are not starting with the assumption of artificial propulsion and working backwards. We are starting with observations, with data, with measurements that do not fit the natural explanation. The acceleration is real. The missing gas cloud is real. These are facts, not speculation. The artificial propulsion hypothesis is not the starting point. It is where the data is pushing us when the natural explanations fail to account for what we are seeing. Let me be very precise about what we are and are not claiming. We are not saying 3I-ATLAS is definitely artificial. We are saying the post-perihelion observations are inconsistent with the natural comet hypothesis given the measured acceleration. That is a scientific statement. It is testable. It makes predictions. If 3I-ATLAS is a natural comet that accelerated through outgassing, then there must be a massive gas cloud around it, and we should detect that cloud in upcoming observations with the Webb telescope, with JUICE, with ground-based instruments when 3I-ATLAS is closest to Earth on December 19th. If the cloud is not there, if December observations confirm what the November 5th images are suggesting, then the natural comet explanation has a serious problem. This is why the November 5th images matter so much. They are our first post-perihelion look at the object. They are the first test of the predictions made based on the acceleration data, and they are not showing what the natural comet model predicts. Not even close. The tail should be there. The massive coma should be obvious. The evidence of 13% mass loss should be unmistakable. Instead, we see an object that looks remarkably similar to how it looked before perihelion, before the supposed massive outgassing event. Think about the sequence of events here. 3I-ATLAS coasted through space for millions or billions of years. It entered our solar system. It was discovered in July. For months it showed no acceleration, behaving exactly like an inert object following a purely gravitational trajectory. Then it approached the Sun, passed perihelion on October 29th, and suddenly accelerated. The acceleration was measured. The math was done. Physics says this requires massive mass loss. But the images taken just a week later show no evidence of that mass loss having occurred. That sequence does not make sense if this is a normal comet. Something about our understanding is wrong. Either the acceleration measurements are wrong, which seems unlikely given the robustness of the data, or our interpretation of what should cause that acceleration is wrong, or 3I-ATLAS is not a normal comet. The comparison with Comet Lemon really drives this home. Lemon is out there doing comet things, making a nice tail, looking exactly like we expect a comet to look. 3I-ATLAS, which should be far more active based on the acceleration data, looks less active than Lemon. How does that work? How do you accelerate more but outgas less? The obvious answer is you use a propulsion method that does not require massive outgassing. You eject material at much higher velocity, so you need less of it. Or you use some method that does not involve ejecting material at all. But now we are back to talking about technology, about artificial systems, about the hypothesis that makes people uncomfortable. And I understand the discomfort. Truly. The history of astronomy is filled with supposedly anomalous observations that turned out to have mundane explanations. Every time we see something unusual, jumping straight to aliens is generally not the smart bet. The smart bet is natural phenomena we do not fully understand yet. So why is this different? Why is Avi Loeb, a respected Harvard astrophysicist, taking the artificial hypothesis seriously here? Because the natural explanations are not just incomplete, they are contradictory to the observations. The math demands one thing, the images show another, and that contradiction cannot be hand-waved away. We have 2 more months of critical observations coming. JUICE is observing 3I-ATLAS right now. The spacecraft is in a unique position to see the object post-perihelion from a vantage point impossible from Earth. The data from those observations should be transmitted back by February. Ground-based telescopes will get another look in early December, when 3I-ATLAS emerges fully from solar conjunction. And on December 19th, 3I-ATLAS makes its closest approach to Earth, just 269 million kilometers away. That is when Hubble and Webb will have their best shot at detailed spectroscopy, at measuring the composition and density of any gas cloud surrounding the object. Those December observations are going to be definitive. If there is a massive gas cloud, Webb will detect it. Webb can measure the composition, the density, the mass of the gas. We will know if 13% of the nucleus mass is out there in a cloud surrounding the object. And if it is not there, if the December observations confirm the November 5th images, then we have to seriously reconsider what 3I-ATLAS actually is. Because at that point, the natural comet explanation is not just weak, it is ruled out by the data. The November 5th images are not the end of this story. They are the beginning of a new chapter, one where the easy assumptions are no longer tenable, where the object refuses to behave the way our models predict, where every new piece of data seems to deepen the mystery rather than resolve it. The tale that never came is not just a curiosity. It is a challenge to our understanding, a signpost pointing towards something we have not encountered before. And in about 6 weeks, on December 19th, we are going to find out just how deep this mystery goes. Congress demands answers while NASA goes silent. While the astronomical community was processing those November 5th images, something unprecedented was happening in Washington. Representative Anna Paulina Luna from Florida's 13th District did something that rarely occurs in the intersection of politics and space science. She went public with her frustration over NASA's refusal to release data about 3I-ATLAS. Not just any data. Specific high-resolution images that could answer fundamental questions about what this object actually is. On November 4th, Luna submitted her second letter to NASA regarding 3I-ATLAS. The first letter, sent back on July 31st, had proposed something ambitious, redirecting the Juno spacecraft from its Jupiter orbit to intercept 3I-ATLAS when it passes within 53 million kilometers of Jupiter in March 2026. That proposal included detailed trajectory analysis showing that a specific thrust applied on September 14th could position Juno for a close encounter, all for an estimated cost of $15 million for a 6-month mission extension. But by October, Luna's tone had changed dramatically. The second letter was not about future missions. It was about data NASA already possessed but refused to share. The specific request is remarkably precise. Luna demanded the highest resolution high-rise camera images from the Mars Reconnaissance Orbiter taken on October 2nd and 3rd with 30 km per pixel resolution. She also requested any supplementary data from Mars missions that detected unusual activity when 3I-ATLAS passed within 30 million kilometers of Mars around October 3rd, and she asked for observations from the Parker Solar Probe, Hubble, and the James Webb Space Telescope. These are not vague requests. These are specific instruments, specific dates, specific datasets that should exist if the missions were operating as planned. The timing of this shift from Luna's first letter to her second tells you everything about what happened behind the scenes. In July, she was optimistic about collaboration, about redirecting existing assets to study this object. By October, she realized NASA had been observing 3I-ATLAS extensively, but refusing to share the findings with the scientific community and the public. That is not speculation. That is what the letter explicitly states. NASA has the data. NASA is not releasing it, and a member of Congress is now demanding to know why. Avi Loeb sent his own request directly to Professor Alfred McEwen at the University of Arizona, the principal investigator for the HiRISE camera team. As of his article publication, he had received no response. Think about that. The lead scientist on arguably the highest resolution camera that photographed 3I-ATLAS during its Mars flyby is not responding to inquiries from one of the most prominent astrophysicists in the world. Either McEwen is bound by some directive not to discuss the data, or there is another reason for the silence. Neither option is particularly comforting. The high-rise images are scientifically crucial. With 30 km per pixel resolution, they represent approximately 3 times better resolution than Hubble's best public image from July 21st, for an object whose size is still uncertain, whose surface properties are unknown, whose composition is debated. That resolution could be transformative. The brightest pixel in the high-rise images would provide the best constraint yet on the actual area of the nucleus. We could determine if 3I-ATLAS is truly the 5 km diameter solid object that some estimates suggest, or something else entirely. We could look for surface features, for jets, for any asymmetries that might explain the acceleration. But we cannot do any of that without access to the images. The controversy exploded into mainstream consciousness when Kim Kardashian tweeted at NASA Administrator Sean Duffy asking for clarification about 3I-ATLAS. Her tweet was simple, direct, and reached her hundreds of millions of followers. Wait, what's the T on 3I-ATLAS? Question marks and exclamation points. Duffy's response was reassuring in tone but notably evasive in content. Great question, he wrote. NASA's observations show that this is the third interstellar comet to pass through. Might be aliens. The former is a conclusion. The latter is science. Representative Luna's involvement represents something deeper than just one congressperson being curious about space. Luna sits on committees with oversight authority. Her questions are not casual. Her letters are formal congressional inquiries when a member of Congress demands that a federal agency release data collected with taxpayer dollars that creates pressure that did not exist before. NASA can ignore Avi Loeb's emails. it cannot as easily ignore congressional inquiries, especially when those inquiries become public and generate media attention. The government shutdown that began in October complicated everything. NASA's official website stopped updating. The usual channels for data release went dormant. The Public Affairs Office that normally handles media inquiries shut down. This created a perfect storm of opacity right at the moment when 3I-ATLAS was passing through its most scientifically interesting phase. Was the shutdown simply unfortunate timing, or was it convenient? That question is above my pay grade, but the timing certainly prevented the normal flow of information that usually accompanies major astronomical events. Despite the shutdown, some data continued to flow. Raw imagery from the Perseverance rover on Mars remained accessible through automated systems. That is how we got those intriguing images from October 1st and 3rd that might show 3I-ATLAS as a faint smudge in the Martian sky. Astrophotographer Simeon Schmaus stacked 20 images from the Merscam Z camera and found a faint object in the constellation Corona Borealis very close to where 3I-ATLAS should have been. Is it definitive? No. Is it suggestive? Absolutely. But these are raw, unprocessed images from a camera designed to photograph rocks on the Martian surface, not distant comets. The high-rise images, purpose-built for exactly this kind of observation, remain locked away. The scientific community's frustration is palpable. Multiple Mars orbiters had 3I-ATLAS in their sights during the October 3rd close approach. ESA's Mars Express and ExoMars Trace Gas Orbiter did photograph the object. They released some images, fuzzy dots showing 3I-ATLAS against the star field. But these are from cameras designed to image the Martian surface at close range, not objects tens of millions of kilometers away. The resolution is limited. The scientific value, while real, is constrained by the instrument's design parameters. NASA's Mars Reconnaissance Orbiter, on the other hand, has the high-rise camera, built for exactly the kind of long-range, high-resolution imaging that could reveal crucial details about 3I-ATLAS. Those images exist. They were taken on October 2nd and 3rd when 3I-ATLAS was just 30 million kilometers from Mars, and they are not being released. Why would NASA withhold scientific data about an astronomical object? There are several possible explanations, and not all of them involve conspiracy or cover-up. One possibility is that the images require extensive calibration and processing before release, and the government shutdown interrupted that process. Mars images go through multiple pipeline stages before they are considered science-ready. Background subtraction, flat fielding, geometric correction, photometric calibration. This takes time and personnel. If those personnel were furloughed during the shutdown, the pipeline stops. Another possibility is that the images show something unexpected, something that requires careful analysis before public release to avoid misinterpretation. Scientists generally prefer to understand their data before releasing it, especially when that data might generate significant public interest or misunderstanding. If the high-rise images show features that are ambiguous, that could be interpreted multiple ways. NASA might be taking extra time to prepare proper context before publication. A third possibility, the one that generates the most speculation, is that the images show something NASA does not want to discuss yet. Not necessarily aliens or technology, but perhaps something that contradicts previous public statements, or something that would require admitting uncertainty where certainty was claimed. Bureaucracies do not like admitting they were wrong. They especially do not like admitting uncertainty when they previously projected confidence. If the high-rise images raise more questions than they answer, releasing them creates a public relations problem for an agency already under scrutiny. The controversy highlights a fundamental tension in how space agencies operate. NASA is both a scientific organization and a government bureaucracy. Those two identities do not always align. Science demands transparency, immediate data release, open debate about interpretations. Bureaucracy demands careful messaging, controlled narratives, avoiding statements that might later need correction. When an object like 3I-ATLAS comes along, something genuinely anomalous and unexplained, that tension becomes acute. Do you release data immediately and accept the chaos of public speculation, or do you hold data until you have a clear explanation, risking accusations of secrecy? Representative Luna's demand for transparency is essentially a demand that NASA prioritize its scientific identity over its bureaucratic identity, at least in this case. Release the data, let the scientific community analyze it, Let independent researchers contribute their expertise. Accept that we might not have all the answers immediately, and that is okay. That is how science works. The public can handle uncertainty better than it can handle the appearance of secrecy. Avi Loeb has been consistently vocal about this. His articles, his media appearances, his direct appeals to NASA and ESA for data access. He is not demanding special treatment. He is asking for what should be standard practice in publicly funded science. The data belongs to humanity, not to any single agency or government. When that data concerns a potentially historic object, the only interstellar visitor we will observe this closely for potentially decades, withholding it is scientifically indefensible regardless of the bureaucratic rationale. The Mars Reconnaissance Orbiter cost $720 million to build and launch. It has been operating since 2006, nearly 2 decades of continuous observations. Every dollar of that cost came from taxpayers. The HiRISE camera, one of the most sophisticated imaging systems ever sent to another planet, exists because the public funded it. When that camera photographs something as significant as 3I-ATLAS, the resulting images are not NASA's property to withhold. They are public data, collected with public resources, and the public has a right to access them. Luna's letters represent the public's voice in this. She is doing what oversight is supposed to do, demanding accountability from agencies that operate with public money and public trust. Whether NASA ultimately releases the HiRISE images voluntarily or under congressional pressure, the fact that pressure is necessary at all reveals something troubling about how the agency handles data from anomalous observations. This should not require congressional intervention. This should be automatic. As we wait for the HiRISE images, as we watch this bureaucratic standoff play out, 3I-ATLAS continues its journey through the inner solar system. It does not care about governmental politics or agency rivalries or public relations strategies. It is simply moving, following its trajectory, either expelling gas in ways we have not detected or using some other method to adjust its course. The images that could help us understand which exist in a database somewhere, processed or unprocessed, ready to reveal their secrets, and we cannot see them. Not because they do not exist, not because the observations failed, but because the people who control access to those images have decided, for whatever reason, that now is not the time to share. That is not science. That is something else entirely. The 13% problem. Let me walk you through a calculation that changes everything about how we understand 3I-ATLAS. It is not complicated mathematics. It is not quantum mechanics or relativistic physics. It is basic momentum conservation, the kind of physics you learn in first-year university courses. But the implications of this simple calculation are profound, and they are why the missing tail is not just surprising but potentially paradigm-shifting. When an object accelerates in space without an external force pushing it, that acceleration has to come from somewhere. For rockets, for spacecraft, for anything that changes velocity without gravity doing the work, the acceleration comes from throwing mass in the opposite direction. Action and reaction. Newton's third law. You want to go forward, you throw something backwards. The faster you throw it, or the more of it you throw, the more you accelerate. This is rocket science in the most literal sense, and the math is straightforward. The rocket equation relates acceleration to mass loss through a simple relationship. The force propelling you forward equals your mass loss rate multiplied by the velocity at which you are ejecting that mass. Rearrange that equation, and you can calculate how much mass you need to lose to produce a given acceleration. This is not theoretical physics, this is engineering. We use these equations to design actual rockets, actual spacecraft that carry humans and cargo through space. The math works. It has been tested countless times. There is no ambiguity here. For 3I-ATLAS, the measured non-gravitational acceleration is 1.1 times 10 to the negative 6th astronomical units per day squared in the radial direction away from the Sun, plus 3.7 times 10 to the negative 7th in the transverse direction. Convert those numbers to more familiar units, and you get about 94 kilometers per day squared at perihelion. That is the acceleration we need to explain. That is the number everything else flows from. Now we need to know how long this acceleration was acting. The perihelion passage time is the duration over which 3I-ATLAS was close enough to the Sun for intense heating to occur. That is calculated by taking the perihelion distance, 203 million kilometers, and dividing by the perihelion speed, 68 kilometers per second. Do the division, and you get roughly 1 month. 4 weeks of intense solar radiation, intense heating, intense sublimation if this is a normal comet, doing normal comet things. The last variable is ejection velocity, how fast the gas is leaving the surface. For a comet heated by the sun, this is determined by temperature. The surface temperature of 3I-ATLAS at perihelion, based on its distance from the sun, and assuming it absorbs solar radiation like typical dark icy bodies, would be around 200 to 250 Kelvin. At that temperature, carbon dioxide molecules, the dominant volatile we detected in the coma, have a thermal velocity around 300 meters per second. That is how fast they're moving on average, as they transition from solid ice to gas and escape the nucleus. 300 meters per second is not arbitrary, it is thermodynamics. Plug these numbers into the momentum conservation equation, and out comes the answer. The fraction of mass that 3I-ATLAS must have lost equals the perihelion passage time, multiplied by the acceleration divided by the ejection velocity. 1 month times 94 kilometers per day squared divided by 300 meters per second. Work through the unit conversions and you get 13%. At minimum, 3I-ATLAS had to lose 13% of its total mass during the month around perihelion to produce the acceleration we measured, assuming the acceleration came from ejected gas moving at thermal velocities. 13%. Think about what that means physically. If the nucleus is 5 kilometers in diameter, a sphere of ice and rock with typical cometary density around 500 kilograms per cubic meter, the total mass is roughly 33 billion tons. 13% of that is 4.3 billion tons. 4.3 billion tons of material converted from solid to gas and expelled into space over the course of 1 month. That is an average mass loss rate of over 1,700 tons per second, continuously, for 30 days straight. To put that in perspective, the Webb telescope measured 3I-ATLAS's mass loss rate back in August at 150 kilograms per second. That was when the object was 3.3 astronomical units from the Sun, much cooler than at perihelion. Mass loss rates increase exponentially as comets approach the Sun because sublimation rates depend exponentially on temperature. So yes, we expect the rate at perihelion to be much higher than in August. But we are talking about more than 10,000 times higher, from 150 kilograms per second to over 1,700 tons per second. That is not a gradual increase. That is a phase transition, a complete change in the object's behavior. When you lose 13% of your mass as a comet, you do not do it quietly. That mass becomes a massive cloud of gas and dust surrounding the nucleus. Solar radiation pressure pushes on that dust. The solar wind, the stream of charged particles flowing from the Sun, pushes on the gas. Both forces point away from the Sun, which is why comets have tails pointing anti-sunward. The gas and dust get pushed into a long stream trailing behind the nucleus as it moves. This is not subtle. This is visible from Earth with backyard telescopes when the comet is bright enough and close enough. 3I-ATLAS, at its distance and brightness, should have a spectacular tail if it lost 13% of its mass. The comparison with Comet Lemon is quantitative, not just qualitative. Lemon was photographed by the same observatory on November 3rd showing a clear tail. Lemon is a periodic comet from the inner Oort cloud, a fairly typical icy body following a typical cometary orbit. It was not at perihelion in November, it was well past its closest approach, cooling down, becoming less active, and yet it displayed a visible tail easily captured in the same images that showed 3I-ATLAS without a tail. If 3I-ATLAS was outgassing at the rates required by the acceleration data, its tail should dominate Lemon's by orders of magnitude. Instead, it has no clear tail at all. Now let me address the obvious objection. Maybe the gas is there, but we cannot see it. Maybe it is too diffuse, too spread out, too low in surface brightness for detection. But this does not hold up under scrutiny. We detected the carbon dioxide coma around 3I-ATLAS back in August, using Sphere X, when the object was much farther from the Sun and much less active. Sphere X measured the coma extending out to 348,000 kilometers from the nucleus. That is nearly the distance from Earth to the Moon. If 3I-ATLAS was surrounded by a cloud containing billions of tons of freshly ejected material, a cloud orders of magnitude more massive than what we detected in August, we would see it. The instruments are sensitive enough. The observing campaigns are thorough enough. the absence is real. There is another test we can apply. When comets outgas, they brighten. The dust in the coma reflects sunlight, adding to the light reflected by the nucleus itself. The amount of brightening is related to how much dust is present, which correlates with how much gas is escaping because the gas drags dust particles along with it. 3I-ATLAS did brighten near perihelion, that much is true. The brightness increased by a factor of about 5 between early October and early November, but that brightening consisted with 30% mass loss. After that, compare with other comets that have undergone major advert. When comets fragment or have larger chunks of their nucleus break up, they can brighten by factors of 100 or 1000, sometimes more. The brightness spike is dramatic and unmistakable. 3I-ATLAS brightened by a factor of 5. That is noticeable, certainly, but it is not the massive increase you would expect from losing 13% of your total mass in a violent sublimation event. The brightening we observed is more consistent with modest increases in activity, a thicker coma, more dust, but not the kind of catastrophic outgassing that the acceleration demands. Here is where the propulsion hypothesis starts looking less like science fiction and more like the only explanation that fits the data. Suppose 3I-ATLAS accelerated not through natural sublimation, but through some kind of propulsion system, an engine, a drive, technology. If the exhaust velocity of that system is much higher than 300 meters per second, the required mass loss drops proportionally. Exhaust a propellant at 3,000 meters per second instead of 300, and you only need to lose 1.3% of your mass instead of 13%. Exhaust it at 30,000 meters per second, and you only need 0.13%. The higher the exhaust velocity, the less propellant you burn to achieve the same thrust. Modern chemical rockets on Earth have exhaust velocities around 4,000 meters per second. Ion drives, the most efficient propulsion systems we have built, can reach 50,000 meters per second or higher. If 3I-ATLAS were using something comparable to an ion drive, the actual mass loss could be a small fraction of a percent, far too little to produce a visible tail, but entirely sufficient to generate the observed acceleration. And here is the thing. At those low mass loss rates, you would not expect a massive gas cloud. You would not expect a tail. You would expect exactly what we are seeing, an object that accelerates without obvious outgassing. This is not proof of technology. Let me be absolutely clear about that. This is an observation that the natural explanation requires conditions we're not observing, while the technological explanation makes predictions that match the observations. That does not mean technology is the answer. It means technology is a hypothesis that deserves serious consideration, because the alternatives are not working. Could there be exotic cometary processes we do not understand? Absolutely. Could 3I-ATLAS have some unusual composition or structure that allows it to accelerate efficiently without producing visible tails? Possibly. But we need to propose specific mechanisms, not just wave our hands and say comets are complicated. What specific process would allow 13% mass loss without a visible tail? What composition would exhibit non-gravitational acceleration without detectable outgassing? These are not rhetorical questions. They are scientific challenges. If the natural explanation is correct, we need models that make testable predictions, not appeals to unknown unknowns. The 13% problem is not going away. It sits at the heart of the 3I-ATLAS mystery. Either the object lost that much mass and somehow avoided producing a tail, which violates our understanding of cometary physics, or it accelerated through some mechanism that does not require 13% mass loss, which means it is not a typical comet. Both horns of this dilemma are uncomfortable. Both force us to question assumptions. But discomfort is not a reason to avoid the question. Science advances by confronting observations that do not fit, not by ignoring them because they make us uneasy. In December, when Webb observes 3I-ATLAS at its closest approach to Earth, we will get detailed spectroscopy of the coma. Webb can measure the mass, the composition, the density of gas surrounding the nucleus. If there are billions of tons of carbon dioxide and water out there, Webb will detect them. If the gas cloud is as massive as 13% mass loss requires, there will be no ambiguity. And if the cloud is not there, if December observations show a modest coma inconsistent with the acceleration data, then the 13% problem becomes the 13% crisis. Because at that point, we will have run out of ways to make the natural comet hypothesis work. The math is simple, The observations are clear, and the gap between what should be and what is will demand explanation. Metal without fire, nickel without iron. There is something deeply wrong with the chemistry of 3I-ATLAS, and it has nothing to do with the missing tail. This is about the metal signatures detected in the coma, specifically what was found and what was conspicuously absent. When the Very Large Telescope in Chile turned its spectrographs toward 3I-ATLAS back in August, it detected nickel in the gas cloud surrounding the nucleus. That alone is not shocking. Comets contain metals. They are remnants of the early solar system, or in this case, someone else's solar system, and they carry the chemical fingerprints of their formation. But the spectrum showed nickel without iron. That should not happen in nature. Let me explain why this matters. Nickel and iron are what we call siderophile elements, metal lovers, elements that preferentially bond with metals rather than with oxygen or silicon. They are created together in the cores of massive stars and scattered together when those stars explode as supernovae. The ratio of iron to nickel in the universe is roughly 20:1. For every nickel atom floating around, there should be about 20 iron atoms nearby. This is not a loose correlation. This is one of the most consistent elemental ratios in astrophysics found in meteorites, in asteroids, in the sun, in other stars. Everywhere we look, iron and nickel travel together in predictable proportions, except in 3I-ATLAS. The spectra show nickel emission lines clear and strong, but the iron lines that should accompany them, that must accompany them in any natural object, are absent or far weaker than they should be. The nickel-to-iron ratio in 3I-ATLAS is orders of magnitude higher than in any known comet, including 2I-Borisov, the previous interstellar comet we observed in 2019. 2I-Borisov showed normal nickel-to-iron ratios. It looked like comets are supposed to look chemically. 3I-ATLAS does not. Now here is where it gets interesting. On Earth, when we produce nickel industrially, we often end up with nickel-rich alloys that have been deliberately processed to separate nickel from iron. Stainless steel, for example, is an iron alloy with chromium and nickel added for corrosion resistance. But there are also pure nickel processes, ways of extracting and concentrating nickel while leaving iron behind. One of the most important is the MOND process, which uses a compound called nickel tetracarbonyl. This is a molecule composed of one nickel atom bonded to 4 carbon monoxide molecules. It is highly volatile, meaning it evaporates easily at low temperatures, and it is used to refine nickel to extremely high purity levels. Here is the remarkable thing. The team analysing the Very Large Telescope data suggested that the nickel emission from 3I-ATLAS could be explained by nickel tetracarbonyl in the coma. This molecule breaks apart easily when exposed to ultraviolet light from the sun, releasing nickel atoms and carbon monoxide. That would explain the nickel we're seeing. It would also explain why we are not seeing iron, because iron does not form similar volatile carbonyl compounds under the conditions present in cometary environments. Nickel tetracarbonyl is an industrial compound, a product of deliberate chemical engineering, not something that forms naturally in the cold, low-pressure environment of a comet's surface. Now, before we jump to conclusions, the researchers proposing this did not claim 3I-ATLAS is artificial. They suggested that perhaps, under exotic conditions we do not fully understand, nickel tetracarbonyl could form naturally in interstellar environments or in unusual protoplanetary disks. Maybe. But we need to be honest about what we are proposing here. We are suggesting that an industrial chemical compound, one that requires specific conditions to synthesize on Earth, somehow formed naturally in an object that travelled through interstellar space for millions or billions of years. That is a hypothesis, certainly, but it is not a simple hypothesis. It requires mechanisms we have never observed and conditions we can barely imagine. The alternative is uncomfortable but straightforward. If 3I-ATLAS were manufactured, if it were a technological artifact of some kind, using nickel-rich alloys would make perfect sense. Nickel is stronger than iron in many applications, more resistant to corrosion, better at handling temperature extremes. For a probe or vessel designed to survive millions of years in the radiation-soaked vacuum of interstellar space, nickel alloys would be an excellent choice. And if that object were venting material, either as propellant or through degradation of surface layers, you would expect to see nickel in the emissions without necessarily seeing iron, because the original construction did not use iron-based materials. The nickel-to-cyanide ratio adds another layer to this puzzle. Comets are rich in cyanide compounds. Hydrogen cyanide, cyanogen, various organic molecules containing carbon-nitrogen bonds. These form naturally in the cold environments where comets are born, and they sublimate along with water and carbon dioxide as comets approach stars. 2I showed typical cyanide abundances relative to other volatiles. Its chemistry was unremarkable in that sense, exactly what you expect from an icy body formed in a protoplanetary disk around a distant star. 3I-ATLAS, by contrast, shows a nickel to cyanide ratio orders of magnitude higher than any known comet. There is far more nickel relative to the cyanide than there should be. If this were a natural comet with typical composition, the ratio should be similar to other comets. The fact that it is not suggests either 3I-ATLAS formed in an extraordinarily unusual environment with chemistry unlike anything in our solar system or any other protoplanetary disk we have studied, or the nickel is there for reasons unrelated to primordial comet formation. One of those explanations requires us to invent new astrophysical environments. The other requires us to consider that this object might not be natural. Let me be very clear about the statistical significance here. When Avi Loeb compiled the anomalies of 3I-ATLAS, he calculated the likelihood of each anomaly occurring naturally. For the nickel to cyanide ratio, the probability of this occurring in a natural comet is less than 1%. That is not a hand-wavy estimate. That is based on comparing 3I-ATLAS to the population of known comets, both from our solar system and the one other interstellar comet we have observed. The nickel chemistry of 3I-ATLAS is a 3 sigma outlier at minimum. It is not impossible for natural objects to be outliers, but when you stack multiple 3 sigma anomalies on top of each other, you start running out of probability budget very quickly. The carbon dioxide composition adds context to the metal chemistry. Webb telescope spectroscopy showed that 3I-ATLAS's coma is 87% carbon dioxide by mass, 9% carbon monoxide and only 4% water. For comparison, most comets in our solar system are dominated by water ice, with carbon dioxide as a minor component. 2I Borisov was more carbon dioxide rich than solar system comets, but still had substantial water. 3I-ATLAS is almost entirely carbon dioxide. That suggests it formed in a very cold environment, far from its host star, where carbon dioxide ices could condense but water remained gaseous or was depleted for some other reason. But here is the puzzle. If 3I-ATLAS formed in an ultra-cold environment rich in carbon dioxide and carbon monoxide, where did the nickel come from? Metals do not condense at those temperatures and pressures. They need to form in much hotter environments, either in the disk closer to the star or through processing in a planetary body that later got disrupted. So we have cold ices indicating formation far from a star, and metals indicating formation or processing in hot environments. These two pieces of evidence point in opposite directions unless something unusual happened during this object's history. One natural explanation is that 3I-ATLAS is a fragment of a larger body that differentiated, that separated into layers with metals sinking to the core and ices remaining on the surface. If that body was disrupted by a collision or tidal forces, fragments could contain both icy surfaces and metallic interiors. As the surface ices sublimate, they could expose metal-rich layers underneath, which would then also sublimate or abrade away, releasing metal into the coma. That could explain nickel emissions from an otherwise icy object. But that explanation has problems. Differentiated bodies are usually much larger than 5 kilometers. They need significant gravity to allow heavier elements to sink while lighter ones rise. Objects the size of 3I-ATLAS do not differentiate unless they are fragments of something much larger. And if they are fragments, we would expect to see evidence of the collision that created them. Irregular shapes, exposed interior layers, compositional gradients from surface to interior. The images we have of 3I-ATLAS do not show any of that. It appears to be a reasonably compact, roughly symmetric object, not an irregular chunk blasted off a larger parent body. The other natural explanation is that 3I-ATLAS accreted in an environment where metallic grains were abundant, perhaps near a supernova remnant or in a region of the galaxy, enriched in metals from previous generations of stellar death. But that does not explain the nickel to iron ratio. Supernovae produce iron and nickel together. Enrichment from stellar processes does not fractionate them. You cannot get nickel without iron unless something separates them after formation. On Earth, we separate them through industrial processes. In space, there is no known natural mechanism to do this at the scale required. The most exotic natural proposal is that nickel tetracarbonyl formed during 3I-ATLAS's journey through interstellar space. Cosmic rays, the high-energy particles that pervade the galaxy, continuously bombard objects travelling between stars. Over millions of years, this radiation can cause chemical reactions that would not happen otherwise. Perhaps cosmic ray bombardment of nickel-bearing grains in the presence of carbon monoxide could synthesize nickel tetracarbonyl, which then remains stable in the cold of interstellar space until the object approaches a star and heats up. This is speculative. No one has demonstrated that this process can occur at meaningful rates. But it is at least physically plausible, which is more than can be said for some other proposals. Stephen Burns, the geophysicist who's been tracking 3I-ATLAS closely, offered another perspective. He looked at the post-perihelion images, saw the missing tail, noted the acceleration, and concluded that 3I-ATLAS is likely a fairly solid chunk of metal and carbon, not a loosely bound pile of ice and dust. If the object is primarily metallic with a carbon-rich coating or matrix, that would explain the nickel emissions, the lack of a massive tail despite acceleration, and the survival of perihelion heating without fragmentation. Solid metal does not sublime the way ice does. It does not produce tails. It does not outgas violently. A metal-rich object could be heated to high temperatures at perihelion and barely react, maintaining structural integrity while a normal comet would be shedding material and creating spectacular displays. But if 3I-ATLAS is a solid metal and carbon body, where did it come from? Natural processes do not make solid metal planetesimals in isolation. Metals are typically found in the cores of differentiated bodies, or as components in chondritic meteorites mixed with silicates and organics. Pure metal bodies require either core remnants from destroyed planets, which we've observed as M-type asteroids, or industrial manufacturing. And if it is a core remnant, why is it so rich in carbon? Planetary cores are iron-nickel alloys, not carbon-rich materials. Carbon concentrates in the outer layers of planets, not the cores. Every natural explanation for the chemistry of 3I-ATLAS requires adding special conditions, unusual environments, exotic processes. Every natural explanation leaves questions unanswered. That does not prove the object is artificial, but it does mean we cannot simply assume it is natural and call it a day. The chemistry demands explanation, and the explanations we have are either incomplete or require us to invoke phenomena we have never observed. The nickel without iron is not just an anomaly. It is a signpost pointing towards something we do not understand. Something that does not fit into our models of how comets form, how they evolve, how they behave when heated by stars. And until we have a natural mechanism that explains this chemistry without requiring industrial processes or impossible coincidences, the question of what 3I-ATLAS actually is remains very much open. What the solar storm should have done. In the days leading up to perihelion, something remarkable happened that has not received nearly enough attention. The Sun threw a coronal mass ejection directly at 3I-ATLAS. This was not a glancing blow. This was not a near miss. Stephen Burns tracked the event in real time and his forecasts were uncannily accurate. A massive halo CME launched from the far side of the Sun on October 21st, aimed precisely at the location where 3I-ATLAS would be during its perihelion passage. The timing was almost surgical. Impact was predicted for 3 to 4 days later, right around October 25th, just days before perihelion on October 29th. Burns had been predicting this for months. Not the specific CME, but the likelihood that solar activity would spike during 3I-ATLAS's closest approach. His reasoning was based on how large objects affect the electrodynamics of the inner solar system. The Sun is not just a ball of hot gas. It is a complex electromagnetic environment, with magnetic fields threading through the photosphere, with plasma currents flowing through the corona, with a delicate balance of forces that can be disrupted by passing objects. 3I-ATLAS, with its massive size and substantial coma, represented a significant perturbation to that environment. Burns predicted the Sun would react, and it did. The CME that launched on October 21st was classified as a halo event, meaning it expanded in all directions from the eruption point on the solar surface. But the geometry of the eruption was skewed in the direction 3I-ATLAS was travelling. This is visible in the SOHO and stereo imagery that captured the event. The bulk of the ejected material, the densest part of the cloud, was heading straight for where 3I-ATLAS would be at perihelion. NASA's models showed the shock front on the left side of the eruption, the main body of the CME on the right, all oriented along the trajectory of the interstellar object. Burns posted his analysis with barely contained excitement. "As many of you know," he wrote, "I have been forecasting for solar activity exactly like this to occur during this time period of 3I-ATLAS's closest approach to the Sun for months now, because of how it is altering the electrodynamics of the inner solar system." Pretty cool to see play out. That statement reveals something important. This was not post hoc rationalization. Burns went on record before perihelion predicting enhanced solar activity, and then it happened. Now let us talk about what a CME does to a comet. Coronal mass ejections are not gentle, they are not subtle. A CME is a billion-ton wave of plasma and magnetic field travelling through space at speeds from 300 to 3,000 kilometers per second. When this hits a comet, several things happen simultaneously. The plasma interacts with the gas in the coma, exciting atoms and molecules, causing them to fluoresce and glow. The magnetic field embedded in the CME wraps around the coma, confining it, compressing it, sometimes tearing tails off and reconnecting them. The pressure of the plasma wind increases dramatically, orders of magnitude above the normal solar wind pressure, pushing harder on any gas and dust surrounding the nucleus. For a comet that is already actively outgassing, a CME impact is like throwing gasoline on a fire. The additional energy excites more sublimation. The increased pressure pushes material away from the nucleus faster and more violently. Tails brighten dramatically. Comets can increase in brightness by factors of 10 or even 100 when hit by a strong CME. Some comets fragment under the stress, unable to hold together against the combination of solar heating and CME pressure. Comet Ison famously disintegrated during perihelion in 2013, shredded by solar tides and the pressure of multiple CME impacts. If 3I-ATLAS is a loosely bound rubble pile, a fragile collection of icy chunks held together by weak gravity, the CME should have done damage. But here is what actually happened. Nothing, or more precisely, nothing we can detect from the observations available. 3I-ATLAS brightened by a factor of 5 between early October and early November. Yes, but that brightening is consistent with normal perihelion heating, without requiring a CME impact to explain it. There was no dramatic outburst. There was no sudden spike in brightness corresponding to October 25th, when the CME should have arrived. There was no tail formation triggered by the plasma pressure. The object passed through perihelion, presumably got slammed by a massive CME, and emerged looking essentially unchanged. This is bizarre. CMEs are incredibly energetic events. They carry immense amounts of energy and momentum. When that energy dumps into a comet's coma, it does not just vanish. It has to go somewhere. It excites atoms, it ionizes molecules, it creates visible light through fluorescence and recombination. We should see those effects. SOHO, Stereo, and GOES 19 were all watching. These satellites observe the Sun continuously. They see CMEs, they see comets, they see what happens when the two interact. If 3I-ATLAS underwent a massive outburst triggered by the CME, those satellites would have caught it. The data would show it. And yet the published analysis of observations from those instruments shows a brightness increase, consistent with distance-based heating, not with a CME-induced explosion of activity. There are a few possible explanations for this non-event. One is that the CME missed. Predictions of CME arrival are not perfect. They are based on models of how plasma propagates through interplanetary space, and those models have uncertainties. Perhaps the main body of the CME passed by 3I-ATLAS without direct impact. But that seems unlikely given the geometry Burns documented and the fact that 3I-ATLAS was in solar conjunction, almost directly between Earth and the Sun from our perspective, right in the predicted impact zone. Another possibility is that 3I-ATLAS is not actively outgassing in the way we expect. If the object is mostly solid, if it does not have significant volatile ices on its surface, then a CME impact would not trigger enhanced sublimation, because there is nothing to sublimate. You cannot energize gas that is not there. A metal-rich body, a solid chunk of carbon and nickel alloy as Stephen Burns suggests, would shrug off a CME impact with minimal visible effects. The plasma would flow around it, the magnetic field would drape over it, but without a massive gaseous coma to interact with, there would be no dramatic brightening, no outburst, no tail formation. This interpretation fits with the missing tail problem. It fits with the nickel without iron chemistry. It fits with the survival of perihelion without fragmentation. If 3I-ATLAS is fundamentally different from normal comets in its structure and composition, then its response to solar heating and CME impacts would also be different. Normal comets are fragile. They are icy. They react violently to heating. 3I-ATLAS is not reacting the way normal comets react. That tells us something about what it is made of, about how it is constructed, about whether it is truly a natural object or something else. There is another aspect to consider. CMEs also dump energy into comets through magnetic reconnection. The magnetic field carried by the CME interacts with any magnetic field present in or around the comet. When field lines of opposite polarity meet, they can reconnect, releasing enormous amounts of energy in a small volume. This is what creates spectacular displays in cometary tails, bright knots of emission where reconnection events are occurring. If 3I-ATLAS has any internal magnetic field, if it contains magnetized materials, the CME impact could have triggered reconnection events that would be visible as bright spots or streamers in the coma. We do not see those either. The absence of magnetic activity is interesting because most natural bodies are not strongly magnetized. Comets are not. They are collections of ice and dust with minimal magnetic properties. But manufactured objects, especially those containing metals and potentially electrical systems, could have significant magnetic fields either from permanent magnets or from current loops. If 3I-ATLAS were a probe or vessel with active or residual magnetic systems, it might have a magnetic field that would interact differently with CMEs than a natural comet would. The fact that we are not seeing dramatic reconnection events could mean either there is no magnetic field, or any field present is not oriented in a way that produces visible effects when the CME hit, or the CME missed after all. The solar storm that should have transformed 3I-ATLAS into a spectacular display passed with a whimper instead of a bang. That non-event is as informative as any positive detection. It tells us 3I-ATLAS is resilient. It is not fragile. It is not easily disrupted by the violent environment near the sun. It withstood heating to temperatures that would boil water if water were present. It withstood plasma pressures that should have stripped away loose material and intensified any ongoing sublimation. It came through perihelion, structurally intact, chemically consistent, and without the tail that all those energetic processes should have produced. Burns noted something else in his analysis. The CME impact coincided with 3I-ATLAS being observable by the Punch satellite constellation, a set of spacecraft specifically designed to image the solar corona and the region immediately around the Sun. Punch captured 134 images of 3I-ATLAS at perihelion, stacked together by researchers to improve signal-to-noise. Those images should show the effects of the CME if they occurred. They should show brightening, tail development, expansion of the coma. The processed images show a compact source, not dramatically different from pre-perihelion observations, despite the object being at its hottest and most stressed moment. The JUICE spacecraft was scheduled to begin observations of 3I-ATLAS on November 2nd, just days after perihelion. JUICE is in a unique position, not from Earth perspective, but from its location in space as it travels toward Jupiter. From JUICE's vantage point, 3I-ATLAS post-perihelion should be in full view, unobscured by the Sun, at a time when the object should be at maximum activity if it is a normal comet recovering from intense perihelion heating and possible CME impacts. JUICE has instruments capable of detecting water, carbon dioxide, carbon monoxide, and other volatiles. It can measure the coma's size, density, and composition. But we will not see that data until February, when JUICE has sufficient downlink bandwidth to transmit the observations back to Earth. That delay is frustrating but understandable. JUICE is still relatively close to the Sun, using its high-gain antenna as a heat shield. It can only communicate through its medium-gain antenna, which has much lower data rates. Science data accumulates on board faster than it can be sent home, creating a backlog that will not clear until the spacecraft moves further from the Sun and can reorient for high-rate communications. So we wait. We know JUICE observed. We know it captured potentially crucial data about 3I-ATLAS post-perihelion and post-CME. But we cannot see what it saw until February. The pattern emerging is consistent. Solar heating does not produce the expected effects. CME impacts do not trigger outbursts. Perihelion passage does not lead to fragmentation or dramatic tail development, every prediction based on the natural comet model fails to match observations, and every failure to match is another data point suggesting 3I-ATLAS is not what we thought it was. The solar storm should have done something. They should have energized the coma, brightened the tail, maybe even disrupted the nucleus. They did none of those things. And that absence of expected effects is becoming as loud a signal as any positive detection could be. The 10 anomalies in the lobe scale. Avilobe created a ranking system for interstellar objects, a scale from 0 to 10 that quantifies how likely an object is to be artificial rather than natural. 0 means definitely natural, something we understand completely through conventional astrophysics. 10 means definitely technological, unambiguous evidence of design and manufacture. Most objects obviously cluster near 0. Asteroids are 0. Regular comets are 0. 2I Borisov, the previous interstellar comet, scored a 1. Slightly unusual in a few properties, but overwhelmingly consistent with natural formation. 1I Oumuamua, the first interstellar object ever detected, scored much higher, around 6 or 7 depending on which anomalies you weight most heavily. Its cigar shape, its tumbling motion, its acceleration without visible outgassing, all of these pushed it up the scale into territory where natural and artificial hypotheses compete roughly equally. 3I-ATLAS now ranks at 4 on the lobe scale. That puts it squarely in the middle ground, more anomalous than 2I Borisov, less mysterious than 1I Oumuamua, but definitely strange enough to warrant serious investigation beyond casual observation. A ranking of 4 means the probability of natural origin is still higher than artificial, but not by a comfortable margin. It means we cannot dismiss the artificial hypothesis without addressing specific observations that do not fit natural models. It means this object deserves the full attention of the scientific community because it might be teaching us something profound, either about exotic natural processes we have not imagined, or about the reality of technological artifacts from other civilizations. The ranking is based on 10 documented anomalies, each with its own probability of occurring naturally. Let me walk through them systematically because the cumulative weight of these anomalies is what drives the ranking, not any single extraordinary feature, but the pattern of multiple unusual characteristics appearing together in one object. Anomaly 1. The trajectory alignment. 3I-ATLAS follows a retrograde orbit aligned to within 5 degrees of the ecliptic plane, the disk containing the orbits of the major planets. For an object arriving from random directions in the galaxy, the probability of being this close to the ecliptic by chance is about 0.2%, 1 in 500. That is unusual but not impossible. Plenty of natural objects beat 1 in 500 odds. The problem is when you start multiplying these probabilities together as additional, anomalies stack up. Anomaly 2. The sunward jet. During July and August, 3I-ATLAS displayed an anti-tail, a jet of material pointing toward the sun rather than away from it. Normal comets sometimes show features that look like anti-tails from certain viewing angles, but those are optical illusions caused by perspective. The anti-tail of 3I-ATLAS was real, not geometric. It represented actual material streaming sunward, pushed by the pressure of outflowing carbon dioxide from the nucleus overwhelming the outward pressure of sunlight and solar wind. This happened when the object was still far from the sun, still relatively cool, which makes the physics even more challenging to explain. Anomaly 3. The mass and speed. The nucleus of 3I-ATLAS is roughly 1,000,000 times more massive than 1I Oumuamua, and about 1,000 times more massive than 2I Borisov, while moving faster through the galaxy than either of them. The probability of detecting an interstellar object this large and this fast before detecting many smaller and slower objects is less than 0.1%. Our detection biases favour finding smaller, slower objects first, because they spend more time in the inner solar system where our surveys operate. Finding 3I-ATLAS so early in the era of interstellar object detection is statistically surprising. Anomaly 4. The arrival timing. 3I-ATLAS reached perihelion on October 29th, passing within tens of millions of kilometres of Mars on October 3rd, and achieving close approaches to Venus and Jupiter as well, all while being unobservable from Earth during the critical perihelion period due to solar conjunction. The probability of an object from a random interstellar trajectory achieving this specific geometry is about 0.005%. 1 in 20,000. Again, not impossible, but increasingly unlikely when added to the other anomalies. Anomaly 5. The nickel to iron ratio and nickel to cyanide ratio. The gas plume around 3I-ATLAS contains detectable nickel, but no corresponding iron, despite these elements being produced together in stellar nuclear synthesis and found together in all natural solar system objects. The nickel to cyanide ratio is also orders of magnitude higher than any known comet, including 2I-Borisov. The probability of this chemistry occurring in a natural comet is estimated below 1%, based on comparison with the known comet population. Anomaly 6. The water content. 3I-ATLAS contains only about 4% water by mass, far lower than typical comets, which are often 50% water or more. 2I-Borisov was water-rich, consistent with formation in a protoplanetary disk where water ice is abundant. 3I-ATLAS is carbon dioxide dominated, suggesting formation in an extremely cold environment or some process that depleted water preferentially. While not impossible naturally, the extreme depletion adds to the cumulative strangeness. Anomaly 7. The extreme negative polarization. When light reflects off 3I-ATLAS, it exhibits polarization properties never before seen in any comet. The degree of polarization and its wavelength dependence do not match models of dusty cometary comae. This could indicate unusual dust grain properties, unusual composition, or unusual geometric structure. The probability of natural dust producing this signature is unclear because we have no comparison objects, but it's certainly anomalous relative to the comet population we have studied. Anomaly 8. The brightening and blue colour. Near perihelion, 3I-ATLAS brightened significantly and shifted colour toward blue wavelengths. For a natural comet, blue colour is unexpected because dust scatters red light more efficiently than blue, causing comets to appear reddish. The surface of 3I-ATLAS should also be much colder than the Sun's photosphere, producing redder reflected light. The blue colour could be explained by ionized carbon monoxide emission for a natural comet, or it could indicate a hot engine or artificial light source for a technological object. Anomaly 9. The non-gravitational acceleration without a corresponding massive gas cloud. This is the 13% problem discussed previously. The acceleration requires substantial mass loss if caused by natural outgassing, but the post-perihelion observations do not show the required gas cloud or tail. The probability calculation here is tricky because we are still waiting for definitive measurements from December observations, but the preliminary data suggest a significant discrepancy between predicted and observed outgassing. Anomaly 10. The lack of visible tail post-perihelion despite passing through the most intense solar heating and being hit by a major coronal mass ejection. This combines the missing tail issue with the CME impact that should have triggered enhanced activity. Natural comets under those conditions invariably produce visible tails. 3I-ATLAS does not, despite all the energy input that should drive massive sublimation. This is perhaps the most visually striking anomaly, because it directly contradicts what we see when we look at normal comets under similar conditions. Now here is the critical point about the Loeb scale. It is not about any single anomaly being impossible to explain naturally. Almost any individual anomaly can be accommodated with some creativity in modelling. Maybe the trajectory alignment is just luck. Maybe the sunward jet is a weird geometric effect we do not understand yet. Maybe the metal chemistry is from an exotic formation environment. Take any one anomaly in isolation, and you can probably construct a natural explanation that works within known physics. The problem is explaining all 10 anomalies simultaneously, with a single coherent natural model. Each ad hoc explanation you add to accommodate one anomaly makes the overall story more complex, more contrived, less likely. At some point, the accumulated unlikelihood of the natural explanation exceeds the unlikelihood of the artificial explanation, and Occam's razor starts cutting the other way. The simplest explanation that fits all the data might be that 3I-ATLAS is not natural, not because any single piece of evidence is conclusive, but because the pattern as a whole points consistently in that direction. This is exactly how science is supposed to work when confronted with anomalous data. You do not immediately jump to extraordinary conclusions, but you also do not ignore patterns that emerge from multiple independent observations. The Loeb scale is an attempt to quantify that process, to move the discussion from subjective feelings about what seems likely to objective probabilities based on actual data. A ranking of 4 means we are past the point where casual dismissal is appropriate. It means this object warrants dedicated study, careful analysis, and serious consideration of hypotheses that would be premature for objects ranking 1 or 2. Let me address the obvious objection. We've only observed 3 interstellar objects total: 1I Oumuamua, 2I Borisov, and 3I-ATLAS. With such a small sample size, how can we claim any of them are anomalous? Maybe interstellar objects are just weird compared to solar system objects. Maybe we have not seen enough to know what is normal and what is not. This is a fair point, and it is one reason why the Loeb scale uses probabilities rather than absolute classifications. We do not claim 3I-ATLAS is definitely artificial. We claim it has properties that are improbable for natural objects based on what we know about natural objects, both in our solar system and in protoplanetary disks around other stars. The physics of comet formation is not arbitrary. It is governed by thermodynamics, by chemistry, by the processes that occur in disks of gas and dust around young stars. Those processes are universal. They do not change from one star system to another in ways that would produce completely different chemical signatures or dynamical properties. If 3I-ATLAS formed naturally, it formed through processes we can model, processes that make predictions about composition, structure, behavior. When multiple predictions fail to match observations, that is information. That is the universe telling us our models are incomplete or wrong in some fundamental way. The alternative is to assume every anomaly has an independent explanation that happens to make the object look artificial without it actually being artificial, that the trajectory alignment is coincidence, that the metal chemistry is exotic but natural, that the missing tail is some unknown cometary physics, that the acceleration without mass loss is a measurement error or misinterpretation, that the sunward jet is a geometric effect, that the blue colour is ionized molecules. Pile up enough of these independent, unlikely explanations and you end up with a scenario far more complex and improbable than simply proposing the object is technological. The Loeb scale ranking of 4 is not a conclusion. It is an assessment of where we are based on current data. As more observations come in, the ranking could move. If December observations show a massive gas cloud consistent with the acceleration, the ranking drops, maybe back down to 2 or 3. If December observations confirm the missing tail in the absence of gas, the ranking climbs, possibly to 5 or 6, entering territory where the artificial hypothesis becomes competitive with natural explanations. The scale is dynamic. It updates as evidence accumulates. That is its strength. It forces us to continuously evaluate what the data is telling us, rather than locking into a position based on prior assumptions. 4 out of 10, midway between definitely natural and definitely technological. Suspended in the uncomfortable space where neither explanation is fully satisfying, where the data pushes us away from conventional interpretations but does not yet give us enough to embrace unconventional ones. That is where 3I-ATLAS sits right now. That is where we sit as observers, watching an object that refuses to behave, that challenges assumptions, that might be natural or might be something we have never encountered before. And in 6 weeks, when the Webb telescope gets its detailed look, we will find out which direction on the Loeb scale this object is moving. JUICE sees what Earth cannot. Right now, as you listen to this, the European Space Agency's Jupiter Icy Moons Explorer is looking at 3I-ATLAS from a vantage point impossible for any Earth-based telescope. JUICE began its observation campaign on November 2nd, just days after perihelion, and continued through November 25th. The spacecraft is roughly 60 million kilometers from 3I-ATLAS, close enough for meaningful observations but far enough to be safe from any potential debris or unexpected behavior. And critically, JUICE is not looking at the object. The peak heating, the maximum activity, we missed all of that. But JUICE did not miss it. JUICE was positioned to observe 3I-ATLAS immediately after perihelion, when the object should be at maximum brightness, maximum outgassing, maximum everything. The instruments JUICE is using are not opportunistic cameras grabbing snapshots. They are sophisticated spectrometers and imaging systems designed for completely different purposes, but capable of being retargeted for this unexpected opportunity. The submillimeter wave instrument, SWI, built under the leadership of the Max Planck Institute for Solar System Research, can detect water vapor. It operates in the submillimeter wavelength range, specifically sensitive to the rotational transitions of water molecules. If 3I-ATLAS is surrounded by a massive cloud of water vapor from perihelion outgassing, SWI will detect it. The instrument can measure not just the presence of water, but the abundance, the temperature, the velocity of the molecules, giving us a three-dimensional picture of how gas moves away from the nucleus. The Janus Visible Imager should provide photographs of 3I-ATLAS in multiple wavelengths, allowing color analysis and morphology studies. Is the coma symmetric? Are there jets or filaments indicating localized outgassing from specific regions of the nucleus? Does the object show any signs of rotation or tumbling? These questions can be addressed with good quality imaging from JUICE's vantage point. The MAJORS infrared spectrometer can measure the composition of the coma in the near infrared, detecting molecules like carbon dioxide, carbon monoxide, methane, and various organic compounds that would be present if 3I-ATLAS has typical cometary composition. But here is the challenge. JUICE is currently close to the Sun from its own perspective, using its large high-gain antenna as a heat shield to protect sensitive electronics from solar radiation. That means the spacecraft can only communicate with Earth through its smaller medium-gain antenna, which has a much lower data rate. Science data accumulates on board faster than it can be transmitted home. JUICE is collecting observations of 3I-ATLAS right now, storing them in its onboard memory, but we will not see any of that data until February at the earliest, when the spacecraft has moved further from the Sun and can reorient to use the high-gain antenna for high-speed downlink. This creates an agonizing waiting period. We know JUICE observed. We know the instruments captured data during the optimal window for detecting post-perihelion activity, but we cannot see what they saw for another 3 months. It is like being told there is a sealed envelope containing the answer to a crucial question, and you have to wait 90 days before you are allowed to open it. The answer exists. It is recorded. It is just not accessible yet. What are we hoping JUICE will find? If 3I-ATLAS is a natural comet that accelerated through massive outgassing at perihelion, JUICE should detect an enormous cloud of gas surrounding the nucleus. Specifically, it should detect water vapor and carbon dioxide in quantities consistent with at least 13% mass loss from a 5-kilometer nucleus. That translates to billions of tons of material. SWI is sensitive enough to detect water at those levels easily. If the gas is there, JUICE will see it. If the gas is not there, JUICE will confirm its absence with high confidence. The submillimeter wave instrument is particularly interesting because it can measure gas that is invisible to optical telescopes. Water vapor does not emit visible light efficiently. You need infrared or submillimeter wavelengths to see it. That is why Spherex and Webb, operating in infrared, were able to measure the carbon dioxide coma back in August, while optical telescopes like Hubble could not. JUICE's SWI extends that capability into the submillimeter regime where water emission is strongest. If there is a hidden gas cloud around 3I-ATLAS that somehow escaped detection in optical wavelengths, SWI is the instrument most likely to find it. There is another aspect to JUICE's observations that matters beyond just detecting gas. The geometry of JUICE's viewing angle, relative to 3I-ATLAS and the Sun, allows measurement of the gas distribution in 3 dimensions. From Earth, we see the object more or less along the Sun to comet line. We see the coma from the front looking back toward the Sun. JUICE sees the coma from the side. This perspective reveals whether gas is being expelled symmetrically in all directions or preferentially in specific directions. If 3I-ATLAS has a propulsion system producing directed thrust, that thrust would create an asymmetric gas distribution, more material expelled in one direction than others. JUICE's side view is ideal for detecting that kind of asymmetry. Now let's talk about what it means if JUICE does not detect a massive gas cloud. If the February data release shows that 3I-ATLAS emerged from perihelion without the billions of tons of water vapor and carbon dioxide that the acceleration requires, we have a major problem for the natural comet hypothesis. At that point, we will have pre-perihelion observations showing modest outgassing, acceleration measurements requiring massive outgassing, and post-perihelion observations showing no evidence of massive outgassing. That timeline does not work for natural sublimation. It works perfectly for a propulsion system that activated near perihelion, provided thrust, and then shut down. The Particle Environment Package, PEP, is another JUICE instrument relevant to 3I-ATLAS observations. PEP measures charged particles, electrons and ions in the local space environment. When comets outgas, some of the gas gets ionized by solar ultraviolet radiation, creating a population of charged particles around the nucleus. The density and composition of these ions tells us about the outgassing rate and the composition of the parent molecules. If 3I-ATLAS underwent massive outgassing, there should be a detectable population of ions surrounding it, measurable by PEP even from JUICE's distance. If those ions are absent or present at levels inconsistent with the required outgassing, that is more evidence the acceleration was not caused by natural sublimation. JUICE's observation campaign also benefits from extended duration. The spacecraft observed 3I-ATLAS for nearly 4 weeks, from November 2nd to November 25th. That is not a brief snapshot. That is continuous monitoring allowing detection of changes over time. If the coma is evolving, if gas is dispersing or condensing, if brightness is fluctuating, JUICE will capture that evolution. Multi-epoch observations are far more valuable than single snapshots because they reveal dynamics, processes, how the object responds to changing solar heating as it moves away from perihelion. There is also the possibility of coordination with other spacecraft. NASA's Europa Clipper mission, currently on its way to Jupiter, could potentially observe 3I-ATLAS if its trajectory and instrument pointing allow. Clipper carries its own suite of spectrometers and cameras designed for studying Europa's icy surface, but capable of observing other targets when opportunities arise. If Clipper observed 3I-ATLAS around the same time as JUICE, we would have 2 completely independent data sets from 2 different vantage points, allowing cross-validation and stereo reconstruction of the coma structure. As of now, we do not know if Clipper attempted observations, but the possibility exists. The Max Planck Institute researchers involved in the JUICE campaign have expressed both excitement and caution. They never expected to observe an interstellar object during JUICE's 8-year journey to Jupiter. This is a target of opportunity, a bonus science return that was not part of the mission's original plan. That means the observations were set up quickly, without years of preparation and optimization that normally go into planetary mission observations. There is risk that the pointing was not perfect, that the exposure times were not optimal, that some data might be noisy or incomplete. But even imperfect data from JUICE is better than no data at all, and the instrument teams did everything possible to maximize the quality of observations given the constraints. Ladislav Rezak, the project lead for SWI, called the encounter an extraordinary stroke of luck. "We never expected anything like this," he said, and he is right. The probability of JUICE being in the right place at the right time to observe 3I-ATLAS post-perihelion is tiny. If 3I-ATLAS had arrived a year earlier or later, JUICE would not have been positioned for good observations. If the trajectory had been slightly different, the viewing geometry would not have worked. But the timing aligned, the geometry worked, and now we have data sitting in JUICE's memory waiting to be downloaded and analysed. February feels like a long way off. It is more than 2 months from now as of this recording. By February, 3I-ATLAS will have made its close approach to Earth on December 19th. We will have Webb observations, Hubble observations, ground-based campaigns. We will have a much more complete picture of the object's state post-perihelion. JUICE's data will arrive in the context of all those other observations, either confirming what we learned from Earth-based assets or revealing discrepancies that will need to be explained. What if JUICE finds something no one expected? What if the data shows structures in the coma that cannot be explained by natural outgassing, geometric patterns or emission signatures inconsistent with sublimation physics? We have to consider that possibility, not as the likely outcome, but as a potential outcome that would change everything about how we interpret 3I-ATLAS. The spacecraft is looking at the object from an angle we cannot replicate from Earth. It is using instruments sensitive to wavelengths we cannot easily access from the ground. It might see things we have not seen, things we cannot see, things that definitively answer whether this object is natural or something else. Until February, we wait. We speculate. We analyse the data we have while knowing that crucial information exists but remains inaccessible. JUICE's observations represent our best chance to definitively test the natural comet hypothesis during the critical post-perihelion window. If those observations support the hypothesis, the mystery of 3I-ATLAS takes a step toward conventional resolution. If they contradict it, we enter new territory where assumptions break down and extraordinary possibilities demand serious consideration. The answer is already recorded. It is travelling through space at the speed of light, encoded in radio waves that will reach Earth in February. Until then, 3I-ATLAS keeps its secrets. Observed, but not yet revealed. The propulsion system hypothesis. Let us talk directly about what we have been circling around for 7 chapters. The hypothesis that 3I-ATLAS might be using a propulsion system, that its acceleration is not natural outgassing but directed thrust from some form of engine or drive mechanism. This is not speculation for entertainment value. This is a scientific hypothesis based on observations that do not fit natural explanations. It makes testable predictions. It can be falsified, and whether we like it or not, it is becoming increasingly difficult to dismiss without addressing specific features of the data that point toward it. The basic logic is straightforward. We observe non-gravitational acceleration. That acceleration requires explanation. For natural comets, the explanation is the rocket effect from sublimated gas. But that explanation requires a massive gas cloud that we do not observe. If natural sublimation does not explain the acceleration, we need an alternative mechanism. A propulsion system explains both the acceleration and the absence of a massive tail because technological propulsion can achieve much higher exhaust velocities than thermal sublimation, requiring far less mass expenditure for the same thrust. Adam Hibbard, a colleague of Avi Loeb, pointed out something interesting about the timeline of 3I-ATLAS's behaviour. The object displayed an anti-tail, a sunward jet, during July and August when it was still far from the sun. Then as it approached perihelion, that anti-tail diminished, and a normal tail started to develop in September. The transition from anti-tail to tail is well documented in observations from multiple telescopes. Hibbard noted that if 3I-ATLAS were a spacecraft slowing down using forward thrust, this behaviour is exactly what you would expect. The anti-tail represents braking thrust pointing forward, opposing the object's motion. As the spacecraft completes its deceleration manoeuvre, the thrust reduces or reorients, and the anti-tail disappears. Think about how this maps onto the timeline. 3I-ATLAS entered the inner solar system at high velocity. To achieve the close planetary approaches it managed, to fine-tune its trajectory to pass near Mars, Venus and Jupiter, it would need to adjust its velocity. A braking manoeuvre during approach, reducing speed to allow closer encounters with specific planets, makes strategic sense if you're an interstellar probe designed to survey multiple worlds in a single pass through a star system. The anti-tail during approach could be evidence of that braking thrust. The transition to normal cometary tail as the object swings around perihelion could indicate the end of active manoeuvring, reverting to passive sailing mode for the outbound leg. This interpretation seems far-fetched until you look at the arrival geometry. The probability that a random interstellar trajectory would bring an object within tens of millions of kilometers of Mars, Venus and Jupiter, while keeping it invisible from Earth during perihelion is about 1 in 20,000. Those odds drop further if you require the trajectory to be aligned within 5 degrees of the ecliptic plane, which has another 1 in 500 probability. Multiply those together, and you get odds of 1 in 10 million for the trajectory happening by chance. At that point, the trajectory itself becomes evidence of intentional targeting rather than random passage. If you wanted to design an interstellar mission to survey the inner solar system, how would you do it? You would aim for the ecliptic plane where the planets orbit. You would time your arrival to pass close to multiple worlds of interest. You would use the star, the sun, for gravity assist to bend your trajectory and adjust your velocity without burning fuel. You would do all of this while minimizing the time spent observable from the most technologically advanced planet, Earth, to avoid detection and interference before completing your observations. That mission profile, which makes perfect sense for a probe, happens to match what 3I-ATLAS did. Coincidence or design? The nickel chemistry fits this hypothesis as well. If 3I-ATLAS were manufactured, if it were a probe or vessel built to survive millions of years in interstellar space, nickel-based alloys would be excellent construction materials. Nickel is strong, corrosion-resistant, maintains mechanical properties across wide temperature ranges, and does not become brittle in the cold of deep space the way some metals do. An advanced civilization building interstellar probes would likely use materials optimized for longevity and durability. Nickel alloys meet those requirements, so when we detect nickel emissions without corresponding iron, that could be evidence of alloy outgassing or surface ablation from a manufactured object. The blue colour near perihelion is harder to explain naturally but straightforward technologically. A hot engine exhaust could produce blue light. High-temperature plasmas emit across the visible spectrum but peak in blue wavelengths when hot enough. If 3I-ATLAS activated a propulsion system near perihelion, if that system produced exhaust hot enough to emit visible light, we would see exactly what was observed. A blue shift in the object's colour and consistent with natural dust upward. Far below has been careful to note that ionised carbon monoxide can also produce blue emission in country coding, so the colour alone is optional. But combined with the other anomalies, look better with technological emission than natural fluorescence. Timing of the acceleration is also suggested. 3I-ATLAS showed no non-gravitational acceleration during July, August, and September. Its motion was purely gravitational. Then near perihelion, acceleration appeared. After perihelion, we still detect some acceleration, but at reduced levels. This on and off behaviour is exactly what you would expect from a propulsion system activating for specific manoeuvres and then shutting down. Natural sublimation, by contrast, should increase gradually as the object approaches the Sun, peak at perihelion, and decrease gradually afterward in a smooth, predictable curve. The observed behaviour is not smooth. It is punctuated with distinct changes in acceleration that correlate more with positional milestones like perihelion than with gradual changes in solar heating. Let us address the obvious questions. If 3I-ATLAS is a probe, where is it from? How long has it been travelling? What is its purpose? These are fair questions, and the honest answer is we do not know. Interstellar distances are vast. The nearest star system, Alpha Centauri, is 4.3 light-years away. At 3I-ATLAS's velocity of about 130,000 miles per hour relative to the Sun, it would take tens of thousands of years to cross interstellar distances. If it came from a system 10 light-years away, the travel time exceeds 100,000 years. If it came from further, add proportionally more time. An object built to function after 100,000 years of travel would need to be incredibly robust. No moving parts that could wear out. No electronics that could degrade from radiation exposure. Passive systems, redundant systems, materials chosen for ultimate longevity. It would essentially be a dormant artifact for the vast majority of its journey, activating only when approaching a star system of interest. The anti-tail, the acceleration, the blue glow, these could all be signs of reactivation as the probe entered the Sun's gravitational influence and began executing pre-programmed observation maneuvers. But why send probes at all? Why not just observe from afar using powerful telescopes? Because direct presence gives information telescopes cannot provide. Spectroscopy from light years away can tell you about atmospheric composition, but it cannot tell you about magnetic fields up close, about particle environments, about the subtle details of planetary systems that require in situ measurement. If you want to understand other star systems deeply, you need to go there. And if your civilization has timescales measured in millions of years rather than decades, if you are patient enough to wait for probes to arrive at destinations centuries or millennia after launch, then interstellar exploration becomes feasible. Another question. If this is a probe, why has it not communicated? Why no signals, no obvious attempts at contact? Several possible answers. First, it might not be designed to communicate with us. It might be gathering data for transmission home or storage for later retrieval by follow-up missions. Second, it might be communicating in ways we cannot detect. We monitor radio frequencies, but there are other electromagnetic bands, other modulation schemes, that would be invisible to our current search strategies. Third, it might be malfunctioning. An object travelling for 100,000 years might arrive damaged, still functional enough to manoeuvre but unable to execute communication protocols. Or fourth, and this is important to consider, it might be deliberately avoiding communication. If you are an advanced civilization sending probes to survey other star systems, you might program them to observe without revealing themselves, to gather data about emerging civilizations without interference. The zoo hypothesis in SETI suggests that alien civilizations might intentionally avoid contact with younger species like us, observing but not engaging. A probe following that directive would look exactly like 3I-ATLAS appears to look, manoeuvring for optimal observation angles, passing through the system collecting data, but never transmitting signals that would reveal its artificial nature. The propulsion system hypothesis also makes predictions that can be tested. If 3I-ATLAS is using technology to maneuver, it should continue to show acceleration that does not correlate smoothly with solar distance. As it moves away from the Sun into colder regions where natural sublimation should shut down, technological propulsion might remain active if course corrections are needed for the outbound trajectory. We can watch for that. If acceleration continues well past the distance where cometary activity normally ceases, that is strong evidence for non-natural propulsion. Another prediction relates to the upcoming close approach to Jupiter in March 2026. If 3I-ATLAS is a probe, it might alter course near Jupiter to achieve a specific flyby geometry, or to use Jupiter's gravity for trajectory adjustment. Natural comets follow purely gravitational paths. Any deviation from the predicted trajectory during the Jupiter encounter would indicate active propulsion. Juno's spacecraft, currently orbiting Jupiter, could potentially observe 3I-ATLAS during that encounter if NASA chooses to retarget its instruments. Those observations could be definitive. The hypothesis is also falsifiable, which is crucial for scientific credibility. If December observations show the massive gas cloud required by natural sublimation, the propulsion hypothesis is wrong. If spectroscopy reveals composition consistent with natural comet chemistry, without exotic metal signatures, the hypothesis weakens significantly. If the acceleration ceases completely after perihelion following the expected pattern of sublimation-driven thrust, that supports natural explanations. We are not locked into the technological interpretation. We are proposing it as a testable alternative to natural models that currently fail to explain the observations. Avi Loeb has been explicit about treating this as a scientific question rather than a belief system. He does not claim 3I-ATLAS is definitely artificial. He claims the data is anomalous enough to warrant serious investigation under multiple hypotheses including artificial origin. That is the correct scientific approach. You do not start with conclusions. You start with observations, develop hypotheses that explain those observations, and test the hypotheses against new data. If the artificial hypothesis keeps matching data, while natural hypotheses keep failing, at some point you have to take the artificial hypothesis seriously, regardless of how uncomfortable it makes us. The discomfort is understandable. Accepting that 3I-ATLAS might be a probe means accepting that we are not alone, that other civilizations exist or existed, that they have technology capable of interstellar travel, and that one of their artifacts is currently passing through our solar system, close enough to observe. Those are enormous implications with profound philosophical, religious, and practical consequences. But discomfort is not a reason to reject a hypothesis. If the universe is telling us something extraordinary, we have an obligation to listen rather than dismissing it, because we do not like what we hear. Over the next few months, observations will either support or refute the propulsion hypothesis. Webb in December, JUICE data in February, Jupiter encounter in March. Each provides opportunities to test predictions, to see if the object behaves like technology or like nature. We do not have to wait decades for answers. We do not have to speculate endlessly. The data is coming, the observations are happening, and by spring of next year we will know far more about what 3I-ATLAS actually is than we know today. Until then, the propulsion system hypothesis remains on the table, neither proven nor disproven, but increasingly difficult to ignore as conventional explanations fail to account for what we are seeing. December 19, the final test. On December 19th, 3I-ATLAS will make its closest approach to Earth, 269 million kilometers. That is about 1.8 astronomical units, roughly the distance from the Sun to Mars. By cosmic standards, it is remarkably close for an interstellar object. Closer than 1I Oumuamua ever got during its solar system passage. Close enough for our most powerful telescopes to achieve unprecedented resolution and sensitivity in studying this enigmatic visitor. December 19th is the date that will either resolve the mystery or deepen it beyond anything we have seen so far. Every major observatory with the capability to observe faint objects against the darkness of space will be pointed at 3I-ATLAS that week. The James Webb Space Telescope has observation time allocated. Hubble will be watching. Ground-based facilities across the world will coordinate campaigns to capture photometry, spectroscopy, polarimetry, every measurement technique we have developed for studying comets and asteroids. The International Asteroid Warning Network has been tracking 3I-ATLAS since discovery, and December represents their best opportunity for characterization. This is not one telescope taking a few pictures. This is a full-court press, the astronomical equivalent of throwing every resource we have at a target to extract maximum information in minimum time. Webb's observations are the most critical. The telescope's near-infrared spectrograph can measure the composition of the coma with exquisite precision. If there is carbon dioxide, Webb will quantify exactly how much. If there is water vapour, Webb will detect it down to trace levels. If there are complex organic molecules, metal oxides, unusual compounds we have not considered, Webb's spectral range and sensitivity will reveal them. The data from December will not be ambiguous. It will not leave room for hand-waving or appeals to measurement uncertainty. We will know what is in that coma and how much of it there is. The key question Webb will answer is whether the mass of gas surrounding 3I-ATLAS is consistent with 13% mass loss from the nucleus. That number keeps coming up because it is what momentum conservation requires if the acceleration was caused by natural rocket thrust from sublimated volatiles. 13% of a 5-kilometre nucleus is billions of tons of material. That gas does not disappear. It expands into a cloud that should be easily detectable weeks after perihelion. If Webb measures the gas mass and finds billions of tons present, the natural comet hypothesis survives. If Webb finds orders of magnitude less gas, the hypothesis fails. Let me be specific about what Webb will measure and how. The near-infrared spectrograph splits light into its component wavelengths, creating a spectrum that shows how much light the object emits or absorbs at each wavelength. Different molecules emit and absorb light at characteristic wavelengths determined by their quantum mechanical properties. Carbon dioxide has strong absorption features at 4.3 micrometers. Water has features at 2.7 micrometers. Carbon monoxide shows up at 4.7 micrometers. By measuring the depth and width of these spectral features, you can calculate the column density of each molecule, the amount of that substance along the line of sight from the telescope to the nucleus. Column density combined with angular size of the coma gives you volume density. Volume density integrated over the entire coma gives you total mass. This is not rough estimation. This is quantitative spectroscopy with well-understood physics. The uncertainties are small. If 3I-ATLAS lost 13% of a 33 billion ton mass, the coma should contain at least 4 billion tons of gas. Webb will measure whether that gas is there to within a factor of 2 or better. We will have a definitive answer about whether the predicted mass loss occurred. There is a possibility that makes many people uncomfortable but has to be considered. What if Webb finds almost no gas? What if the coma Webb detects is similar to what Spherex measured back in August? A modest envelope of carbon dioxide with no evidence of massive recent outgassing. At that point we have a fundamental contradiction. The acceleration requires mass loss. The mass loss should produce a detectable gas cloud. The gas cloud is not there. Something in that chain of reasoning must be wrong, and the most likely candidate is the assumption that acceleration was caused by natural sublimation. December 19th is also crucial for optical observations. The object will be well placed in the pre-dawn sky for observers in the northern hemisphere, high enough above the horizon to minimize atmospheric interference. Amateur astronomers with decent equipment will be able to image 3I-ATLAS, contributing to the global observation campaign. The power of distributed observations cannot be overstated. One professional telescope might observe for an hour or two. Hundreds of amateurs observing continuously create a timeline that captures evolution, variability, transient events that might be missed by scheduled observations. We are particularly interested in variability. Does 3I-ATLAS show brightness changes on short timescales? Does the coma flicker or pulse? Are there sudden jets or eruptions? Natural comets sometimes exhibit outbursts, sudden increases in activity caused by exposure of fresh ices or collapse of surface structures. These outbursts are usually accompanied by visible expansion of the coma and increases in tail brightness. If 3I-ATLAS undergoes an outburst in December, we want to catch it. If it shows periodic variation suggesting rotation of an active region, we want to measure that periodicity and infer the rotation period and orientation of the spin axis. The rotation state is actually quite important for distinguishing natural from artificial origin. Natural comets are usually in chaotic rotation, tumbling along multiple axes due to asymmetric outgassing torques. 3I-Oumuamua was tumbling rapidly, completing a rotation every 8 hours with a complex wobble indicating it was not dynamically stable. If 3I-ATLAS shows stable rotation around a single axis with no tumbling, that would be unusual for a natural object but expected for a designed artifact. Spacecraft are usually built with rotational stability, either through symmetric mass distribution or active stabilization systems. A slowly rotating, non-tumbling 3I-ATLAS would fit the probe hypothesis better than the natural comet hypothesis. Polarimetry is another measurement technique that might reveal something unexpected. Polarization measures the orientation of light waves, specifically whether light vibrating in one direction is more intense than light vibrating perpendicular to it. Dust scattering polarizes light in predictable ways depending on particle size, composition, and shape. The extreme negative polarization 3I-ATLAS displayed earlier was anomalous relative to known comets. December observations with better sensitivity might show whether that signature persists, whether it changes as the viewing geometry changes, and whether it provides clues about the physical nature of whatever is producing it. There is also thermal infrared observation. Objects emit heat radiation with intensity and spectrum determined by temperature. A 5-kilometre rocky or icy body at 3I-ATLAS's distance from the Sun should have a surface temperature around 200 Kelvin, maybe slightly warmer on the sunward side. Thermal infrared measurements can test this. If the object is hotter than expected, that might indicate internal heat from radioactive decay, though that is unlikely for a comet, or from active systems if it is technological. If it is cooler than expected, that tells us about surface properties, reflectivity, thermal inertia. The close approach geometry means Earth-based radar could theoretically detect 3I-ATLAS, though the signal would be weak at 269 million kilometers. Radar works by transmitting radio waves at the target and detecting the reflected echo. The strength of the echo depends on the target's size and reflectivity. Large metallic objects produce strong radar returns. Icy or rocky objects produce weaker returns. If 3I-ATLAS has a metallic composition or metallic components, radar might detect it. The Arecibo telescope, which could have made this measurement easily, was decommissioned after its collapse in 2020. The remaining radar facilities like Goldstone have less sensitivity but might still attempt observations. The search for radio emissions is ongoing. SETI organizations have been monitoring 3I-ATLAS for any evidence of artificial signals since discovery. So far, nothing confirmed, though distinguishing faint signals from noise is challenging. December's close approach improves the sensitivity of these searches. If 3I-ATLAS is transmitting radio signals, either communication attempts or leakage from internal systems, December is our best chance to detect them before the object moves away and the signal becomes too weak to distinguish from background. What if December observations show something so anomalous that it cannot be explained by either the natural comet hypothesis or the technological probe hypothesis? What if we see structures, behaviours, emissions that do not fit any existing framework? That is the scenario that keeps scientists up at night, not because we fear it, but because we have no idea how to prepare for it. Science works by building on existing knowledge, extending theories incrementally. Completely novel phenomena require new frameworks, new theories, new ways of thinking about reality. If 3I-ATLAS is something we have never encountered, something our models do not predict and our categories do not contain, December might be when we realise the universe is stranger than we imagined. But let us not get ahead of ourselves. The most likely outcome is that December observations will either confirm or refute the natural comet hypothesis based on gas cloud mass. That binary outcome, presence or absence of the predicted gas, is enough to significantly shift our understanding. Everything else, the rotation, the polarization, the radio searches, those are additional tests that might provide supporting evidence or surprising contradictions, but the gas mass measurement from Webb is the linchpin. It either supports natural outgassing or it does not. There is not much middle ground. Avi Loeb has stated repeatedly that he will accept whatever the data shows. If December observations support natural origin, he will revise his assessment and acknowledge that the anomalies, while unusual, can be accommodated within natural processes. If December observations refute natural origin, he will push for more aggressive investigation, including potential missions to intercept and study the object up close. This is the scientific method in action. You propose hypotheses, you test them, you update your beliefs based on evidence. Ego has no place in this process. Only data matters. The window for meaningful observation extends from early December, when 3I-ATLAS emerges from solar conjunction, through mid-January, when it becomes too faint for detailed spectroscopy. 6 weeks. In that time, we will gather more data on this object than we have for any previous interstellar visitor. We will push our instruments to their limits. We will coordinate across continents and disciplines. And we will answer questions that have been accumulating since July, when a telescope in Chile first spotted an object that would challenge everything we thought we knew about comets, about interstellar visitors, and perhaps about our place in the universe. December 19th is the date, the final test, the moment of truth. What happens if we are wrong? There are 2 ways we could be wrong about 3I-ATLAS, and the implications of each are profound. We could be wrong in thinking it is natural when it is actually technological. Or we could be wrong in suspecting it might be technological when it is actually an exotic but natural object. Both errors carry consequences, not just for this specific case, but for how we approach the next interstellar visitor, and the one after that, and the fundamental question of whether we are alone in the universe. Let us start with the first scenario. Suppose 3I-ATLAS is indeed a probe, an artifact from another civilization, and we fail to recognize it as such. Suppose December observations show anomalies we dismiss as measurement errors or unknown natural processes. Suppose we convince ourselves that the missing tail can be explained, that the nickel chemistry has some exotic natural origin, that the trajectory alignment is just coincidence. Suppose we let this object pass through our solar system, complete its observations or whatever its mission entails, and leave without us ever confirming what it actually was. What have we lost? First, and most obviously, a once-in-a-lifetime opportunity to study extraterrestrial technology up close. The nearest star is 4 light-years away. Even if we detected a radio signal tomorrow confirming intelligent life exists, we could not visit them with current technology for thousands of years. But 3I-ATLAS, if it is technological, is here now. It is accessible. We could potentially send a fast spacecraft to intercept it, study it, maybe even retrieve samples or components for analysis. That opportunity exists for a limited time. 3I-ATLAS is moving at over 100,000 miles per hour. Every day that passes, it gets further away, harder to reach, until eventually it's beyond the capability of any mission we could launch. NASA considered redirecting Juno, currently orbiting Jupiter, to observe 3I-ATLAS during its March flyby of the giant planet. That mission would cost $15 million for a 6-month extension. $15 million is nothing in space agency budgets. It is a rounding error. For that price, we could get high-resolution imagery, spectroscopy, potentially even radar mapping from Juno's instruments, as 3I-ATLAS passes within 53 million kilometers of Jupiter. The proposal was serious, technically feasible, and incredibly cheap for the potential scientific return. If we do not fund missions like this, if we let budget constraints or lack of imagination prevent us from investigating anomalous objects, we deserve to remain ignorant. But the loss goes beyond just this one object. If we fail to recognize 3I-ATLAS as technological when it is, we establish a pattern of dismissing evidence because it does not fit comfortable narratives. The scientific community prides itself on following evidence wherever it leads, but that is easier said than done when the evidence points somewhere uncomfortable. Mainstream acceptance of the artificial hypothesis requires overcoming enormous institutional inertia, career risk for scientists who advocate it publicly, and genuine uncertainty about how to interpret ambiguous data. Those barriers are understandable, but they can also blind us to truths we would rather not see. 3I-ATLAS will not be the last interstellar object we detect. Our survey capabilities are improving. Upcoming facilities like the Vera Rubin Observatory will detect interstellar visitors regularly, maybe several per year. Some will be clearly natural, some will be ambiguous like 3I-ATLAS, and statistically, if technological probes exist at all, some will be unambiguously artificial. If we develop a habit of explaining away anomalies rather than investigating them rigorously, we risk missing first contact not because the evidence was not there, but because we refuse to look at it honestly. Now consider the second scenario. Suppose 3I-ATLAS is natural, an exotic comet with unusual but explicable properties, and we invest enormous resources investigating it under the assumption it might be technological. Suppose December observations reveal the gas cloud we predicted, confirming natural outgassing caused the acceleration. Suppose the nickel chemistry turns out to be some rare but natural process we had not considered. Suppose every anomaly resolves into conventional astrophysics once we have enough data. What have we lost in that scenario? Honestly, not much. We would have conducted a thorough, multi-wavelength observational campaign on an interstellar object, gathering data that advances our understanding of comet composition, structure, and behaviour, regardless of whether the object is natural or artificial. We would have tested our instruments, refined our techniques, practiced coordinating international campaigns on fast-moving targets. We would have learned about exotic natural processes that could inform our understanding of protoplanetary disk, chemistry, interstellar dust grain evolution, and volatile transport in cold environments. Even if the technological hypothesis is wrong, the science we do testing it is valuable. The asymmetry is striking. If we treat 3I-ATLAS as possibly technological and we are right, we gain access to extraterrestrial technology and confirmation that other civilizations exist. If we treat it as possibly technological and we are wrong, we still gain scientific knowledge about natural processes. But if we assume it is natural and we are wrong about that, we lose a historic opportunity that may not recur in our lifetimes. The risk-reward calculation overwhelmingly favours investigation under the technological hypothesis, even if that hypothesis has low prior probability. This is essentially a version of Pascal's wager applied to astrobiology. The payoff for correctly identifying artificial objects vastly exceeds the cost of investigating natural objects mistakenly thought to be artificial. Therefore, we should err on the side of investigation, of taking anomalies seriously, of funding missions that might seem wasteful if the object turns out to be natural, but would be invaluable if it turns out to be artificial. There is also a deeper philosophical point here about how we relate to the cosmos. For 400 years since the scientific revolution, we have been discovering that humanity is not central, not special, not the point around which the universe revolves. We are not at the centre of the solar system. The solar system is not at the centre of the galaxy. Our galaxy is not special among galaxies. This process of demotion from cosmic centrality has been called the Copernican principle, and it has been enormously productive scientifically. It forces us to assume we are typical, unless proven otherwise, which leads to testable predictions about what we should observe. But there is one realm where we still act as if we are central, as if we are special. We assume we are alone. We assume technological civilizations are so rare that we are likely the only one in the galaxy, maybe the only one in the observable universe. This assumption has no empirical basis. It is not derived from data. It is a holdover from pre-scientific thinking, a kind of anthropocentric exceptionalism that contradicts everything else we have learned about our place in the cosmos. If planets are common, if organic chemistry is common, if the building blocks of life are common, why would technological intelligence be unique to Earth? The Drake equation, formulated in 1961, attempts to estimate the number of communicating civilizations in the galaxy by multiplying together factors like star formation rate, fraction of stars with planets, number of habitable planets per star, fraction where life develops, fraction where intelligence evolves, and so on. The equation is more a framework for thinking than a calculation, because most of the terms are highly uncertain, but even conservative estimates suggest there should be many technological civilizations in the galaxy, if such civilizations have lifespans long enough to overlap with us in time. The Fermi paradox asks where these civilizations are if they exist, if intelligence is common, if technological development is a natural outcome of evolution, if even a small fraction of civilizations develop interstellar travel, then the galaxy should be teeming with artifacts, probes, settlements. We should see evidence everywhere. The fact that we do not is called the paradox, and it has generated dozens of proposed solutions ranging from the idea that intelligence is actually extremely rare, to the idea that civilizations inevitably self-destruct before achieving interstellar capability, to the idea that they exist but deliberately avoid contact with primitive species like us. 3I-ATLAS might be part of the answer to the Fermi paradox. Maybe civilizations do send probes, but the probes are designed to be subtle, to observe without being obvious, to gather data without interfering. A probe mission that spans hundreds of thousands of years cannot rely on active communication with the home civilization. The probe must be autonomous, programmed with decision rules about when to reveal itself and when to remain hidden. If the rule is to avoid detection by emerging civilizations, then 3I-ATLAS's behaviour makes sense. It manoeuvres just enough to achieve optimal observation geometry, but not so aggressively that its artificial nature becomes undeniable. It emits just enough anomalous signatures to be interesting but not conclusive. It exists in that liminal space between natural and artificial, where skeptics can dismiss it, and believers can point to evidence, but no one can prove the case definitively either way. This ambiguity might be intentional. A truly advanced civilization would understand that first contact is traumatic, that revealing the existence of superior technology to a younger species can cause social disruption, cargo cult behaviour, loss of confidence in indigenous technological development. Maybe the zoo hypothesis is correct. Maybe we are being observed but not contacted, and 3I-ATLAS is calibrated to be detectable by a civilization at our level of sophistication, but not so obvious that we cannot plausibly deny its artificial nature if we choose to. Or maybe this is all overthinking, and 3I-ATLAS is just a weird comet that happens to have accumulated a perfect storm of unusual properties by coincidence. Maybe there are natural processes we have not imagined that explain everything. Maybe the universe is not as strange as we are making it out to be. That is possible. It is even likely if you go by base rates and prior probabilities. Natural objects vastly outnumber artificial ones in the universe by any reasonable estimate. But likely is not the same as certain, and when the implications of being wrong are as profound as they are. Here, likely is not good enough. We need to know. The next few months will provide data that moves us toward knowing. Not certainty, probably, but significant Bayesian updates in one direction or another. If December shows a massive gas cloud, if JUICE data confirms normal cometary outgassing, if the rotation is chaotic and the chemistry resolves into natural processes, the probability of artificial origin drops dramatically. If December shows no gas cloud, if JUICE sees anomalies, if rotation is stable and chemistry remains inexplicable, the probability of artificial origin rises to the point where we can no longer responsibly ignore it. Either way, 3I-ATLAS changes the conversation. It forces us to take interstellar visitors seriously, not just as scientific curiosities, but as potential probes, as possible emissaries from civilizations we have not met. It establishes precedent for how we should investigate future objects that display similar anomalies. It pushes the discussion of extraterrestrial intelligence out of the realm of abstract speculation and into the realm of practical observational astronomy. That shift is overdue. We have been searching for radio signals for 60 years through SETI programs. We have found nothing confirmed, though that is not surprising given the vastness of space and the narrowness of our searches. But maybe we've been looking in the wrong place. Maybe the evidence is not in radio signals beamed across light years. Maybe it is in physical objects that visit us, objects that can be photographed, studied, potentially even touched. Maybe first contact happens not through a message but through an artifact. And maybe that artifact is already here, has been here since July, is leaving in a few months unless we act to study it more thoroughly. What happens if we are wrong? If we underestimate 3I-ATLAS, we miss history. If we overestimate it, we do good science and remain humble about the limits of our knowledge. The asymmetry is clear, the choice should be obvious, the data is coming, and very soon we will know whether we live in a universe where we are alone, or a universe where others have visited, observed, and moved on while we argued about whether the visit actually happened. I know which universe I find more exciting, and I suspect deep down you do too.